Now recently I've been working on an electronic driver, which I have right here, for my homemade electric motor. And I'm still working on this. There's still a bunch of components that I need to solder onto this board. But today we're going to take a look at what this is and how it actually works, because someone specifically requested that I make a video about building a new driver for my homemade switched reluctance motor. So here we go. Now, before we get into this, maybe for a little bit of context, it's good to remind ourselves of the very basics of what a switched reluctance motor does when it operates. So here's a clip from my previous video that I think explains this pretty well, and I'm too lazy to repeat it now. So let's say you have a 6-pole SRM. That might look like this. So you have a 6-pole stator with 6 coils on it, and then inside of that you'll have a 4-pole rotor, which is just basically a pure block of iron that is in this case shaped like a plus sign. And so when you energize a set of coils on opposite sides of this stator, then the iron rotor will align itself with those 2 poles. And then once that's done, you can energize the next set of coils, so the rotor will align itself with those, and you keep going like that, and your rotor is spinning round, and you have an electric motor. So really, an SRM driver is just a thing that turns each phase on and off at the right moment. And so you might ask yourself, how hard can it be? And the answer is probably a little bit harder than you think. So let's take a look at the basic circuit that is used in my SRM driver, and actually in most SRM drivers that exist. It is called the asymmetric bridge converter. Now, there are other circuits you could use to drive SRMs as well. Those circuits are designed to somehow save on the number of components. So if you're really constrained in the number of components you can use because you're trying to save money, or you're trying to make something that is extremely small, those circuits might be a better option, but they also compromise on performance. So if you're not trying to be extremely cheap, or you're not trying to make something extremely tiny, generally this is the circuit you want to use. So it consists of 2 switching devices. In this case we're using MOSFETs, and 2 freewheeling diodes right here. And the winding of the motor is located right there. So you have this circuit for each phase on your motor. So in my case the motor is a 3-phase motor, so I have this circuit 3 times on my driver board. If I had a 4-phase motor, then I would need this circuit 4 times. That's how it works. Okay, so how does this actually operate? Well, the basic idea is pretty simple. You might already see what's going on here. If you turn both these MOSFETs on simultaneously, then that allows current to flow from the positive rail of the power supply through this MOSFET, then through the winding of the motor, through this MOSFET at the bottom again, and then into the negative supply rail down there. So energizing that particular phase. And then when you turn those MOSFETs off again, also simultaneously, what happens is, of course, there is still energy stored in that magnetic field. There is current flowing through that coil. That current needs to go somewhere, and that's what those diodes are for. So what will happen is, because the current can no longer pass through this MOSFET and no longer pass through that MOSFET, is the electric current will actually flow from the negative supply rail through this diode at the bottom, then into the motor winding right here, where it keeps going in the same direction that it already did, and then pushed up through this diode at the top, back into the positive supply rail, actually recharging the power source a little bit. So the energy that was stored in the magnetic field of the winding is recovered and put back into the power supply. Now this is good for a couple of reasons. First of all, it's good for efficiency because we're recovering the energy, right? Makes sense. But also because it makes the current decay relatively quickly, because this current, as it pushes back into the power supply, it sort of has to fight that supply voltage. In this case, we're going to run this on 24 volts, and therefore the current decays to 0 relatively quickly. Which is good because in an SRM, if your phase remains energized for too long, then it's actually going to start holding things back again, and it makes the motor less efficient. So when you turn that phase off, you want it to be off as quickly as possible. So you want the current to decay very rapidly, and this allows you to do that. So that is essentially one cycle of powering one phase of an SRM. Now, just a quick side note, realize how this is not an inverter, because the current through this winding is never sent in the opposite direction. It's never reversed, because we don't need to do that. We don't need to deal with magnets that have north and south poles in this type of motor. We're just switching the phase on or off. So a lot of people refer to, or use the terms motor drive and inverter interchangeably, which in a lot of cases is fine, because most motor drives are inverters. But this type of motor drive is not an inverter, so keep that in mind. Okay, so something else you can do is something called soft switching. So what we just did with switching both MOSFETs at the same time is called hard switching. Soft switching is when you only switch one of the MOSFETs. So for example, what I could do is, let's say I start by turning on both MOSFETs, allowing current to flow through the winding like this. And then, instead of turning both off at the same time, I only turn this one off. I leave the one at the bottom turned on. Well, in that case, the current can still pass through this MOSFET. And so instead of the whole, going back into the power supply thing that we just saw, the current will now just run in circles. So it'll go here, through this MOSFET, then back through this diode, and then back up to the top of the winding and just keep going like this for a while. So in this case, the decaying of that current will be much, much slower, because the current doesn't have to fight that supply voltage. It only has to fight the resistance of the winding, the resistance of the MOSFET, which are very small, the voltage drop across the diode, which again is also very small, so it can just happily keep running in circles for a while, and there's rarely anything holding it back. So it takes a long time for the current to decay in this scenario. And also, there is no energy recovery into the power supply, right? In this case, the energy is just burned up in the resistance of these components. So this soft switching is usually done to control the power that's delivered by the motor. Because of course you don't just want to switch the phases on and off, you also want to control how much power the motor produces, how much current goes to this phase. And so that's usually done using soft switching by applying PWM, or pulse width modulation, right? Oh, that's an ugly PWM waveform, to the MOSFET at the top. So what you do typically in an SRM is, when you turn a phase on, you start by turning on both MOSFETs at the same time, which allows current to build up through the winding like this. And then you're going to be switching the one at the top on and off rapidly to control how much current flows through the winding. So if you look at the current, it'll go, kind of like this. And then once the rotor reaches the correct position, you want to de-energize that phase. Then once again you switch both MOSFETs off. You do the hard switching thing. The current drops back to zero very quickly, and you move on to the next phase. So this is usually done when you're driving an SRM, right? If you want to turn a phase on or off entirely, you switch both MOSFETs, you do hard switching. But while that phase is energized, to moderate how much current is in that coil, you do rapid switching on only one of the MOSFETs to regulate the amount of current in that winding. Okay, so that's the very basics of driving an SRM. This is actually no different from how I did it in the old driver that I made as well. The big difference between the old driver and the new one is how these MOSFETs are being driven. Because driving MOSFETs is one of those things that seems incredibly simple. You just apply a voltage to its gate and it turns on, but it's not quite as simple as just hooking up a MOSFET to a pin on a microcontroller and calling it a day. There's actually some things you need to take care of to do it properly. So let's take a closer look at this circuit and see how these MOSFETs are being switched. The way this board is built up is, right here you've got the power input, so this is connected to the battery or whatever is going to power the motor. and then here you connect the motor phases on this side of the board. The power stage is on the right side with the transistors and the diodes going on the bottom of the board, so that I can use the case that I'm going to mount this in as a heatsink for those MOSFETs and those diodes. And then on the other side of the board over here, we've got all the control, driver, and the small electronics essentially are on this side of the board. And then in the center here, you've got a bunch of capacitors to store some energy, which of course is also pretty standard to have on motor drivers. Alright, so we've already talked about the power stage, so you can see it on the schematic as well. We've got a MOSFET at the top, a MOSFET at the bottom, and then the motor winding is connected in between them. There is also two diodes. You can see that part down here, so we've got the MOSFET there, a MOSFET there, and then you've got your two diodes over here as well. Now we've also got a shunt resistor which sits over here in the schematic, which is this thing, and that can be used by the controller to measure the current through the winding, which we can use for at least overcurrent protection, but maybe also if we want to be really fancy, we could use it to make like a current control system or something like that. I'm not entirely sure yet, but at least we have the ability to measure the electric current using that shunt. So now the next question is, how do we drive those MOSFETs? Well, the thing is, we use this bit of circuitry right here, which involves a MOSFET driver. And the MOSFET driver is this IC that you see sitting here. So each phase has its own driver. So there is one driver here, and one driver here. The driver that I'm using is the IR2113. There's a lot of other MOSFET drivers that would work too. It's just one that was available and it was cheap, so I got it. And it gets the job done. So before we discuss the details of how this circuit works, perhaps it's a good idea to talk about what's important when you're driving a MOSFET. So the thing about driving a MOSFET is there's two things that are very critical. So first of all, you need the right voltage to drive it. So can you drive a MOSFET from 5 volts, like let's say one of the pins on the Arduino that controls the thing? Sure you can, but a lot of MOSFETs like to be driven with a little bit more than 5 volts. The IRF3205, which is the MOSFET that we're using, can be driven using 5 volts, but its resistance will be lower if you use a higher gate voltage. So we're using about 10 to 12 volts on the gate, which will give us a nice low on resistance and therefore make the MOSFET run as cool as possible. Of course, you could also apply too high of a voltage to the gate and kill the MOSFET. So make sure if you're going to drive a MOSFET, don't apply too much gate voltage either, because that's also not good. The second thing you need to think about when you're driving MOSFETs is you need to switch them on quickly. So the gate of that MOSFET will have some capacitance, and that capacitance will take some time to charge. And if you don't charge that capacitance quickly enough, it switches on too slowly, and if your MOSFET switches on slowly, you're going to get high switching losses, the thing is going to get very hot, and eventually it's probably going to break, depending on how much power you're trying to send through it. So you want to make sure that you switch the MOSFET on very quickly. And so you need something that can drive drive a lot of current into that gate to charge that capacitance as quickly as possible. And that's something that these MOSFET drivers are very good at. So this particular driver is able to supply, I think, up to 2.5 amps of current, which is quite a lot actually. Right, so with that in mind, let's take a look at this circuit. So first of all, you can see that we've got the gate of these two MOSFETs wired up to the MOSFET driver right here, so that the driver is able to turn on both of these MOSFETs. Now, the MOSFET at the bottom is the easiest one to drive. So you just need to apply, like in our case, around 12 volts onto the gate. So how do we do that? Well, here is a resistive divider. You can see we've got two 1K resistors splitting our 24 volt supply into a 12 volt supply, which is here, with a large 22 microfarad capacitor acting as a buffer, and that gives us a 12 volt supply. That 12 volt supply comes in right here, is connected to the input on our MOSFET driver, so the MOSFET driver can simply apply that 12 volts to the gate of our MOSFET to turn it on when we want to. For the MOSFET at the top, things are a little bit more complicated because its source is not connected to ground. Its source is connected to the top of our motor winding. And so when it turns on, when the whole thing turns on, the source of this MOSFET is not going to be at 0 volts like this one. It's going to be at almost 24 volts because it's at the top of the circuit, which means if we want to drive its gate to 12 volts, that needs to be 12 volts on top of the 24 volts that its source is at. And so we would need to drive that gate at about 35-ish volts, which we don't have because we don't have a 35 volt supply. So how is this done? Well, this is done using a so-called Bootstrap capacitor, which is sitting right here. So here's a 470 nanofarad capacitor, which can be charged through a little diode which sits right here, diode D4 in this case. So what happens is, when the high side MOSFET is turned off, its source will be connected to ground because the low side will probably be on. If it's not on right now, it'll be on soon. And so it's going to be connected to ground through the winding of that motor and the low side MOSFET. So because the source is now at ground, this capacitor is going to be charging. It's going to be charging through that diode. So the current will flow from our 12 volt supply and charge this capacitor through this diode. Then, when the high side MOSFET is turned on, its source is going to rise from 0 all the way up to 24 volts. And in the process, the capacitor is still connected to that same source. So the capacitor, which now has been charged to 12 volts, gets lifted up along with that source voltage, giving us a voltage of around 34 volts on that capacitor, which is not able to leak back into the circuit because the diode is preventing it from discharging in this way. And then the MOSFET driver can apply that 34 volts to the gate of our MOSFET. So it's a very clever little solution. Effectively, we're using a charge pump to drive the MOSFET. This is a very typical way of driving high-side N-channel MOSFETs, by the way. So now we know how the MOSFET driver is able to drive those MOSFETs. The next thing we need is to know how we tell that MOSFET driver when it needs to do that. And this happens using these inputs right here. So on the driver we've got two inputs. They're labeled high in and low in, and by applying 5 volts to one of these inputs, you will enable the corresponding MOSFET. So if you apply 5 volts to high in, it'll turn on this MOSFET. If you apply 5 volts to low in, it'll turn on that MOSFET. So what you could do is just tie those pins directly to something like a microcontroller, right? We're using a little Arduino because I'm familiar with that one and it's easy to program. I should probably use something that is more suitable for motor drives, but for now I've decided to just use this. We might change that to something else for a new version later on. So what you could do is you could just tie those pins directly to your microcontroller and just drive them like that. In which case we would need 6 pins for this driver, because each phase will have 2 microcontroller pins, so you'd use 6 of them in total. But we're doing something a little bit different. So, of course, what we want to do is turn on both MOSFETs, or turn off both MOSFETs if we want to energize a phase. And we want to switch the top MOSFET to do our power control, so our PWM switching, soft switching that we talked about. So the way that I've done this is, first of all, the low side MOSFET is controlled using a pin on the microcontroller directly. So you can see that right here. This is labeled commutation 1. And commutation 1 is just a pin on the microcontroller, and it's hooked up directly to the MOSFET driver. And you can see each phase has its own commutation pin. So there is commutation 2 right there, commutation 3 is right there. So that pin will turn on this phase, and this pin will turn on this phase, or at least it'll turn on directly the low side MOSFET. So what about the high side MOSFET? Well, the high in pin is connected to this node right here. It's connected to a transistor, and that transistor is connected to a pin labeled PWM. And PWM is actually just one pin on the microcontroller as well, but it's connected to each phase. So each phase is connected to the same PWM pin. So we're just generating a PWM signal on one pin of our microcontroller. And that's connected to the high-in input of the driver through this NPN transistor. But this NPN transistor is then controlled by the commutation pin as well. So what happens is, if the commutation pin is off, then of course the low side will be off because that one is directly controlled by it. But the high side will also be off because the NPN transistor will remain off, so the PWM signal is not passed on to the high-in input, and so nothing is done to the high side MOSFET. So if the commutation signal for this phase is off, both MOSFETs will be off. If the commutation signal is on, then the low side MOSFET will be turned on permanently, and this NPN transistor will be turned on permanently, allowing the PWM signal to be passed on to this input, which applies that PWM signal onto the high side MOSFET. So therefore you've selected this phase and applied the PWM signal to that MOSFET. So this way we only need 3 pins on a microcontroller to energize each phase, and then we need 1 additional pin to provide a PWM signal which we can apply to all of them at the same time. So I think this is a pretty elegant way of dealing with this. So on another page of the drawings, just get this out of the way, you can see how this is connected. So here is the get this out of the way. Here's the microcontroller itself, or the development board, of course. So you can see here's the commutation pins, and here's the PWM pin connected. And then also you've got the pins for your shunt resistors. Actually, we haven't talked about the shunt resistors yet. So the voltage across the shunt resistor isn't directly connected to the microcontroller. It actually goes through a bunch of amplifiers, which have also I haven't soldered that onto the board yet, but that's going to be right here. There's going to be some amplifiers to amplify that pretty tiny voltage into something that is easier to read by the Arduino, and that will also be applied to these pins right here. So by monitoring the voltage on these pins, the microcontroller will be able to monitor the current in each phase of the motor. And of course the board will also get some inputs over here, which is where you can connect your throttle input and your encoder to monitor the position of the rotor, and that sort of thing. There are some additional pins as well for unplanned use cases. So yeah, that is the motor controller. I think for now what we will do is we'll take this thing and just wire it up for a bit to the scope so that you can see it working. I mean, we can't really spin up the motor yet because I've only done 1 phase on this thing, and there is no heatsink, so we can't really do anything that requires a lot of power. But I can show you on the oscilloscope the driving pulses driving the MOSFETs. So let's just take a look at that, shall we? Okay, so I've connected the motor driver to a power supply, which is sitting right here, and on the other side I've just connected it to the homemade electric motor, which of course is not going to be spinning today because we've only wired up 1 phase. But what we can do is we can use the oscilloscope to view the voltage that is being applied to our MOSFETs. So what I've done is I've programmed the microcontroller to simply apply a 1-second pulse onto this phase. So every second that phase is going to be turned on. And so what we should see when we connect the scope is the low side MOSFET should just be turning on and then off on and then off, every second. And on the high side MOSFET, we should see the same, except also with a high frequency PWM signal applied to it. Within this case, a super low duty cycle, something below 10%. So nothing spectacular is going to happen, hopefully. No magic smoke coming out today, at least not until we put the heatsink on. So let's just start by connecting the scope. We're just going to connect the ground to the actual ground of the circuit right here. And then we're going to connect the probe to the low side MOSFET. So like this. Alright. Then I'm just going to turn on the camera that looks at the oscilloscope. I mean, that's also pretty useful. There it is. Now I'm going to turn on the power supply. And as you can see on the scope, the voltage goes up and down every second. So that's exactly what we expected. So the low side is working properly. Now for the high side, of course, we could just leave the ground connected here and then probe the high side MOSFET. But then the voltage would be going all the way up to, I don't know, 30 volts or whatever. And so it would not fit on the display of the scope, at least with the current settings. So instead, what I'm going to do is connect my ground clamp to one of the diodes, which is right here. So we're now connected, the ground is now connected to the top of the motor winding and to the source of the high side MOSFET. And then I'm going to connect the probe to the gate of the high side MOSFET like this. And this way we can see, at least not yet, because apparently we need to change the settings a little bit. There you go. You can see a very little pulse. It's like, what is it, 10 microseconds long, something like that. So that is our PWM signal being applied. If we zoom out, you can see it's all these little pulses. And so it still turns on every second, but it actually consists of these very, very small PWM pulses. And of course, when you're actually using this to drive a motor, the width of those pulses is going to be controlled by the throttle. So if you increase the throttle, the pulses will actually get wider, and that way the motor will get more power. So anyway, there it is, my new motor driver, which is still a work in progress. I think it's going to work pretty well. It's a lot better than the old one. I think the biggest improvements are that we're using much better circuitry to drive the MOSFETs, which should allow for much faster switching and therefore much lower power losses. We're using these heat-sinked diodes, which should also handle a lot more power than the regular diodes I used before. And of course the layout has just generally improved, allowing me to put roughly the same amount of components or even more on just a much tinier board. And actually this is still a pretty big board compared to, surface mount components. So maybe one day I'll make a better version that uses surface mount components so we can make it really tiny. But for now I'm quite happy with this. So I'm just going to finish assembling this board, and then hopefully sometime soon we can properly test this big old sucker over here. Actually, it's not that big, is it? But it weighs like 3 kilos, so it better make a lot of power to be worth all that weight. Anyway, I hope you've enjoyed this video. It probably turned out to be quite a long one. If you did, maybe consider clicking the like button or subscribing to this channel. And of course, thank you very much for watching.